So this talk is going to be an introduction to neural networks, and specifically neural networks as applied to image data. We're going to talk a little bit about how exactly it is that neural networks are able to classify images so well. So the title is Understanding How Neural Networks See. So it's going to be basically a very brief introduction to artificial neural networks, and my goal is really to get students ready for an assignment on neural networks. We have several papers about that if you want to read the papers kind of about the assignments, and I've given this assignment several times in a neural networks class, machine learning class, and currently I'm teaching a data science class, which probably most of the people watching this lecture are actually in that class. And this is going to be project 4 in SML310. So we're also going to give a very brief introduction to what's called explainable AI. So explainable AI means you have an AI algorithm. Generally, kind of classically, it would be kind of like a black box. In recent years, people are trying to make it so that the AI module does not just output the correct answer, but also gives some indication as for why it is that it chose the answer that it did. So let's start with just kind of a review. So this is the setting for supervised machine learning. So you have a training set, right? So you have x1 up to xn. Each of the inputs in the training set is going to be an m-dimensional vector. So this would be an example. And then you'll also have for each, for example, x2, you'll have an output y2 like this. You also have a test set. So the test set looks just like the training set. The difference is the training set is what we use in order to make our machine learning module. And the test set is data that we're not using in order to train the machine learning module. It's what we use as a representative for new data, right? So if you do well in terms of predicting the right answers on the test set, because you haven't seen the examples in the test set before, it's as if you are working on new data. So you can hope that if you get, for example, 80% correct on the test set, you'll also do well on new data, so you'll get 80% correct on the test set. So one way to think about this is our goal is kind of in the training phase is to find a function h theta such that h theta xi for every xi in the training set is approximately equal to yi. Of course, if y is discrete, there's no approximately equal, so we just say h theta of xi is usually equal to yi. So this is for I for 1 through n, so that's in the training set. And the hope is that if this works on the training set, then for any I, this would also be true. So in particular, it would be true for x's in the test set. And like we said, that the test set is kind of like a proxy for new data because you're not using the test set in order to train your machine learning module. So this h theta is kind of any function that's parameterized using theta, right? So you might imagine if x is some kind of vector, as in the example on the slide, that h theta is, so you'd say h theta of x is like theta 0 plus theta 1 x1 plus theta 2 x2 plus maybe theta 1 x1 squared and so on. So it could be something like that. And the idea is you're trying to find, so the form is fixed, but you're trying to find the thetas which give you the best outputs in the sense that you get the best kind of the answer on average that's as close as possible to yi for every I. Okay, so that's our setting. So one way to think about it is you have this kind of thing, and what you're trying to do, what the machine learning algorithm rather is trying to do, is it's trying to change those thetas a little bit so that this becomes more true on average for the training set. And that's basically kind of like this is kind of why this style of machine learning, so neural networks, but also something like logistic regression, this is why it works, because you can change the thetas a little bit and hopefully get the answer a little bit more right, and then you'll change the thetas a little bit more and hopefully get the answer a little bit more right still. So we can contrast this to kind of programming. So in programming as well, you might have a problem and you have kind of sample test cases. So in the slides here, for example, like maybe double list 0, 0 should be 0, 0, maybe double list 1, 2 should be 2, 4, right? So here there is a bug, but you can't very easily just say, well, I'll just change my code a little bit and maybe then I'll pass all my test cases. So, I think anybody who's in the audience has tried it at least once, and you know that, well, it can be frustrating to work like that, and if the problem is complex enough, it's just not going to work. You need to actually kind of like think about the meaning of your code rather than just kind of like try to fiddle with it a little bit and hope that you pass all the test cases. With Python, that is true because, well, for one, you can't just change like the for to a while. It just won't run because it would be a syntax error, right? So on the other hand, if you change the thetas a little bit, well, it's still going to be a valid h theta at the very least. And what empirically seems to be true is that you can actually kind of just like try to change the thetas. Of course, like you don't do it randomly, although there are algorithms that literally do that randomly. So you don't do it randomly, but still you can kind of try to change the thetas a little bit gradually and hope that on average you get answers that are more and more correct. So let's talk about our task. So one possible task is image classification. So here we have kind of all sorts of pictures of so mostly Canadian musicians. So we have, you know, noted Canadian musician Justin Bieber. We have an ex-prime minister of Canada who does pretty good Beatles covers, actually. You can look it up on YouTube. So how can we make machine learning do that? So the first thing is kind of to a computer, Justin Bieber would just look like a bunch of numbers, right? So what I mean by that is for any image, so here, for example, you have a grayscale image, so imagine that it's 4 by 4 pixels, right? So here you have some darker pixels, here you have some brighter pixels, here you have some pixels that are completely white. You can encode the brightness using a number, so usually it would be between 0 and 255, although you could imagine different scales. So here kind of 255 means white, so 128 means like a gray that's kind of light, so like somewhere in between 0, which is completely black, and 255, which is completely white, and 60 would be kind of like a dark kind of gray. So once you have this image, so to be clear, it's a 4 by 4 image, so kind of the lines here are not really in the image, they're just there to make it easier to understand what's going on. You can convert it to a vector by just reading things in line by line. So this 60, 60 to 55 to 55, that's the first line, and then this is the second line, and then this is the third line, 60, 60, like this, and this is the fourth line. So any two-dimensional image, this way you can just convert to grayscale. So, okay, so again, what's our face recognition task? So we have our training set. So in the training set, you have kind of x1, the vector that represents the first photo, y1, the label, x2, the vector that represents the second photo, y2 is the label, and so on. So the label, in this case, it's like a discrete variable. It's a name. You could, in general, imagine that y would also be a vector. So in the test phase, you have a new input x. So you took an image, you converted it to a vector, and you want to plug it into the machine learning module, so something like h theta, and you hope that you'll get a y. So here you'll notice that the example was like, this is clearly a number. This is not like this is not a name. But if you have two names, you might imagine that if this number is closer to 1, I'll say, well, it's name number 1, and if this output is closer to -1, I'll say, well, that's name number 2. If I have two names, that works. For multiple names, you'll see what to do in a second. So, okay.